Now that we have introduced 4 methods to train a neural network for function inverse problem, the first method is the input-output method, where you have the inputs and the output to the neural network, so you can do a supervised learning directly. And that does not require the PDE itself, so it does not require you to any setting to the PDE numerical servers or any knowledge of the PDE servers. And here in this slide, I represent the comparison of 3 methods which requires PDE information. The first is the residual minimization method. The residual minimization method incorporates all the information into one residual term. The information includes the boundary data, the initial data, the observation, and the governing equation. And after you minimize the residual, you will eventually get optimal weights and biases of the neural network, and then this will hopefully reconstruct your unknown function in the function inverse problem. And the penalty method works like you, instead of solve a system of constraint optimization problem, you solve an unconstrained optimization problem by incorporating the PDE constraints using penalty functions. And in this method, you need to specify the penalty parameters. On the one hand, for penalty parameters, you can use that to weigh your belief about the PDEs or your data. If you believe that your PDE has more model form errors, you can place less weights on that. Or if you believe that your data is very noisy and the PDE should be focused, then you can just use a large penalty parameter on the PDE constraint. However, on the other hand, for those parameters are very tricky. It's actually very difficult to choose in practice which parameter to use, and that's actually a drawback of the penalty method. And the third method that requires PDE information is the physics constraint learning, which is optional in this course. And this is a very powerful and efficient method to do automatic differentiation for nearly all the PDE solvers. And if your neural networks is embedded in your PDE system, which requires a very complex PDE solver to resolve the stability issues, or for high accuracy, or the PDE itself is essentially nonlinear, this method can work in all of those cases. But the difficulty here is that physics constraint learning is much more difficult to implement than the other 2 methods, but it has many other benefits. Based on the data you have, you can have sparse data and many other scenarios we did not touch in this course. So this is a very direct comparison. For sparse observations, we did not talk about that. But we mentioned a little bit about the residual minimization. We did the full field data. You have to know the temperature everywhere in your bar. And for penalty method, you do not need that. And for physics constraint learning, we did not emphasize that, but actually you can do sparse observations. And in terms of easy to implement, the first 2 methods are definitely very easy to implement. And the third aspect is whether they enforce the physical constraints. And this is quite interesting. And you can view this as your belief about the PDE constraints and your belief about data. If your belief is that the PDE constraint is very important and they are correct, and you want to enforce that, you should definitely do that, because if you do not do that, your neural network might converge to a non-physical solution, which is not desirable. It can perform well in fitting your data, but it never captures the physics. And also in terms of fast convergence, which we did not show in class, actually empirically we observe a lot of good convergence results for physics constraint learning, and for penalty methods it may turn a yield condition problem to a worse yield conditioned problem. And also in terms of minimal optimization variables, as we mentioned in penalty method, you have to treat the state variables also as free optimizable variables, and that causes a lot of problem in memories or in computational cost, or they even contributes to the yield conditioning of a penalty method. Yeah, that's a summary for the training method, and for the next few lectures, we will have hands-on experience with solving those kind of inverse problems using automatic differentiation and neural networks.